So continuing from the last class, now we will start DC JFET biasing. So there are three types of JFET biasing configurations. First one is fixed bias, second one is self bias, and third one is voltage divider bias. Fixed bias. So this is the fixed bias circuit where we can see this is the JFET, and with the JFET with drain, there is a drain to source means plus VDD is connected, and then RD drain resistance and the capacitance across the output side, and in the input side a input capacitance C1, a gate resistance RG, and a negative gate voltage VGG whose minus or the negative terminal is connected to gate and plus terminal is connected to source. So here two voltage sources are being used. One is VGG and another is VDD. VGG is reverse bias at the gate to source terminal, thus no current will flow through RG. So no current will flow through RG. So that's why here the JFET is called a voltage control device, not current control device. Then this is the fixed bias circuit. In fixed bias circuit, we can see all the capacitors are replaced with open circuit condition, means across the output there is no capacitor, and only the RD elements, means the resistive elements RD and RG are present along with the supply, that is VDD and VGG, and in same configuration, that is the VGG is connected reverse condition, and VDD is connected in forward. Plus is connected to drain and minus is connected to source. Now if we write KVL in case of loop 1 means if we go to the in circuit, so VGG plus VGS equal to 0, where VGS equal to minus VGG. So and the equation that we have seen in last few classes, the drain current equation ID is equal to IDSS into 1 minus VGS by VGS off, or VGS off is also called VP or V pinch off whole square equal to IDSS into 1 plus VGG by, again it is divided by V pinch off or VGS off condition 2 whole square. So this is the voltage equation we can say, and this is the current equation of the fixed bias circuit. Then output loop, if we write the KVL equation in the output side, it will be minus VDD plus IDRT plus VDS, or in other words we can write VDS equal to VDD minus IDRT where VDS is the drain to source voltage, VDD is the voltage supply given in between drain and source, and ID is the drain current, and RT is the drain resistance. And this type of KVL equation formation has also done in BJT. When we learn BJT, we also do the same thing. So here we are doing the same thing. So our main target is to find the KVL equation for input circuit and KVL equation for the output circuit. Now for making a graph or making a plot, we need to take some values of different parameters that we were discussing few minutes back. So here 16 volt has been taken as VDD, 2 kilo ohm is the RT, and here in the input side or the gate to source side, we have a negative gate voltage of 2 volt and RG 1 mega ohm. We can see that the RG or the gate resistance is very high, so that no current will flow through the gate terminal inside the gate terminal. So only the means voltage difference will be there in between gate and source, and current will be near about 0. Though practically very small amount of leakage current flows everywhere when we are using this kind of high resistance. Now Question is determine the following network VGSQ, IDQ, VT, VG, VS. Now VT equal to VDS equal to 4.75 volt, VG equal to PS equal to minus 2 volt. Now where minus 2 volt is coming from here, as no current is flowing, so there will be no drop across this resistance. So whatever voltage we are providing in the gate, in between gate and source terminal, we will get the same voltage across gate and source terminal. So um, respective to that, we will get minus 2 volt, exactly minus 2 volt across this gate and source terminal. Though in practical cases, some of the voltage will be lost in material, uh, in between the material as heat, but as we are using a very high resistance, that will be very minimum, so we can neglect that losses. So exactly the voltage we will provide in VGG, that will be reflected in across the VGS. Now talking about the ID current, here it is written as IDQ, means the current ID at Q point, so that's why it is written as IDQ. So IDQ is equal to IDSS into 1 minus VGS by VP, that I was talking about. VP is the pinch off, or in some cases it is also written as VGS within bracket off, means in off condition the value of VGS is equal to the pinch off voltage of VP. So 1 minus VGS divided by VP whole square, so that is 10 milliampere. 10 milliampere is, it is written over here, the saturation drain to source saturation current or drain saturation current is 10 milliampere, where the pinch off voltage is minus 8. So we are replacing these values in this equation. So IDSS is 10 milliampere into 1 minus VGS. VGS is minus 2 again. So VGS means get to source voltage, which is, we just now we have discussed that it will be exactly same as the given voltage, as there is no current in the gate circuit. So minus 8 uh, in the numerator, and in the denominator there will be Vp is already given, that is minus 8. So if we find out the value, it will come 5.625 milliampere. So that will be value of ID or drain current at Q point. And after that, VDS is basically the drain to source voltage, or the voltage drop across drain to source terminal, or drain to source junction. So here, as the resistance value is less, so current, obviously the current will flow in this side of the circuit, or of the combination. And here you can see that VDD is equal to VDD minus IDRT. So VDD is 16 volt, ID is the current, drain current. Drain current is, just now we have found out the drain current is 5.625 milliampere, so that we have to use, and along with the 2 kilo ohm RD or drain resistance. So ultimately we will get a drain to source voltage across, the voltage across drain to source voltage at about 4.75 volt. So like this we have to find out, or we have to solve different type of problems. So some of the elements or some of the components will be given, and we have to find the other components in the given circuit. Now we are talking about Q point. So taking these values, that values we have found out from the previous problems, so we have to plot the graph between ID and VGS. So ID and VGS, and as we are using negative VGS, so that's why we will use the minus x-axis for drawing our plot or graph. So in this case, we can see at pinch off, V pinch off minus 8 volt, there will be no current conduction. So the first point will be this one. Then the at medium point, let us say at minus 4. At minus 4, the current will be IDSS by 4, that is 2.5 milliampere. And at Q point, IDQ we have found out, that is 5.625 milliampere. So let us take 5.6 milliampere, and at that, and that will be means that will achieve at which value of VGS? So that will be at -2. When the VGS value is -2, then the current ID will be 5.6 milliampere or 625 milliampere to be exact. So Q point, and that is the Q point, and in between if we take another point to draw the graph, so let us say if Vp by 2 means -4 volt, when the VGS is -4 volt, then your IDSS value will also be get divided by 4, so it will be 2.5 milliampere. So likewise we have to draw the output characteristics between VGS and ID, where this Q point will be uh, denoted like this, and draw load line, and if we draw the load line, and the cross section point will be taken as the Q point. Acha. In previous case we have seen two voltage source were being used, but in this cell bias circuit we will see only single voltage source, that is VDD. No other source will be used. This left side will be taken as the input side, and the right side will be taken as the output side. So in this case cell bias, so as it is cell bias means only single voltage source, and in the gate circuit there is no other separate source. So here if we write the KVL for this side, so it will be VGS plus VRS. VRS means another thing here, a another resistance has been added in the source side also, source terminal also, that is called RS, source resistance. So two in total two resistance, one is drain resistance as previous circuit, and another new resistance has been connected, that is source resistance, and this is RS. So as per the KVL, VGS this value or this voltage plus VRS this voltage is equal to 0. So technically VGS equal to minus VRS, and that can also be written as I means ID into RS. The current ID is into RS. As no current is flowing through this line, so all the ID current will flow through this line. So and this circuit is technically is this RD and RS when it is in turned on condition are in series. So technically whatever current is flowing here, this will be same as this IS. So ID into RS, that drop will be equal to RS, VRS. Okay. And this graphical representation is to denote the previous cell bias circuit with single source, uh, where we can see this is the pinch off and this is the IDSS. Now VGS is 0 at ID equal to 0, VGS minus ID RS at this point. So Vp by 2. So as per the value of different the IDSS or Vp or VGS, so this graph can be drawn. Let us see if there is any. Yes. So this is a means at different VGS, as here Vp or the pinch off voltage is not given, and IDSS is not given. So that's why it is written like this. 0 at 0 IDSS value of current will come, at 0 IDSS value will come, then at 0.3 means 30% of Vp IDSS by 2, 30% of Vp, let us say here somewhere here, so 30% of, so it will be half around over here, and then at 0.5 50% of Vp means here it will be 1/4 of IDSS, then at Vp it will be completely 0. So no conduction, current conduction will happen at pinch off voltage. So likewise we have to draw the characteristics and load line to point out the Q or Q point. Here this is the load line, this is the characteristics, and this is the Q point. So this is one Q point, this is this is not the Q point, this is the Q point, as the cross section of the VI characteristics and the load line is the Q point. So here the JFET in cell bias configuration will work efficiently. Okay, so these are some equations. ID equal to IDSS by 2 for this one that we have already discussed. VGS equal to minus IT into RS, we have also discussed this one. And if we replace this ID by IDSS by 2, so it will be minus IDSS into RS divided by 2. Now in the right side of the circuit, VDS equal to VDD minus ID into RS plus RT. Now what I was talking about, that this is a series circuit, so the ID current will be same in RS and RD, and the series total resistance of the path will be RS plus RT. So that's why VDD, that is the supply voltage across drain and source, minus ID drain current or the current through the device into RS plus RD. So so VDS is VDD minus ID into RS plus RD. So same thing also is written over here. The Shockley's equation for these combinations also, these biasing circuit also. Achha, example same. So self bias example. So here also it is given that as in this side there is no supply, so no supply has been given in this side, and the VDD value is 20 volt, RS value is 3.3 kilo ohm. Sorry, RS. I'm wrong. RD value is 3.3 kilo ohm. RS is 1 kilo ohm. So and IDSS value is again 8 milliampere, and VP pinch of voltage is minus 6 volt. So we have to determine this value, along with we have to draw the characteristics and find out the Q point. So VGSQ. So move on. See, VGS is equal to minus ID into RS. When ID is 4 milliampere, VGS is minus ID into RS, means minus 4 milliampere into 1 kilo ohm. 1 kilo ohm into is equal to minus 4 volt. When ID is 8 milliampere, VGS equal to minus ID into RS. So minus ID into, again same formula, 8 milliampere into RS. RS is again 1 kilo ohm. So it will be minus uh, 8 volt, minus 8 volt. Okay, so here this device means this is the VP minus 6 volt. In minus 6 volt the current is 0. Then at 0, sorry, so at 0 VGS, when there is no gate to source voltage, the current is maximum, or the saturation current is 8 milliampere, and in the middle somewhere that 50% of VP, that means if it is minus 6, means at minus 3 volt, of VGS, we are getting 4, means 4 volt, sorry, 4 milliampere of, sorry, 2 milliampere of current. And similarly at 30% of VP, as expected here, so you will get near about, means 4 milliampere of current. And by getting this point, we can draw this characteristics or transfer characteristics of JFET in cell bias configuration. Moving on. So here, this is the graph, this is the load line basically.